Our last speaker this evening is going to be Dr. Mark Burgman, and then after he finishes, we'll have a chance to address some questions or discussion with all of you about any aspects we've talked about of conservation planning. Thank you.
Thank you. Thanks very much for sticking around. I'll be brief, and I guess it's my job to try and describe what it is about uncertainty that sits inside the framework described by the first three speakers. And I'm going to talk about some of the same things that they talked about, but I'm going to put inside that framework an explicit consideration of what we mean by uncertainty. There's a standard taxonomy. There are many taxonomies, but there is one standard taxonomy that's used by engineers and other physicists, all sorts of other people who are not biologists, ecologists, conservation biologists. Essentially, they regard two kinds of uncertainty: variability, naturally occurring, unpredictable change. If I go and measure a stream, if I put a thermometer in the stream and I measure it, and then I take the thermometer out and put it back in again, I'll get a different value. And if I measure in a slightly different place in that stream, I'll get a different value. That's because the stream doesn't have a single temperature, it has a set of temperatures, and we characterise that with an average and a standard deviation or variance. So it's a process that we can characterise as a variable process. Now, if we continue to measure that more and more frequently, that level of variation doesn't become any less. We understand it better, but it stays the same. It's inherent in the system itself. That's what we mean by natural variability, naturally occurring unpredictable change. Engineers call it aleatory uncertainty if you're looking in an engineering journal. And then there's a thing called lack of knowledge. Lack of knowledge means I just don't know what the fact of the matter is. I have a stream, it's variable in its temperature, in time and in space, but even so, I'm measuring it imprecisely because my thermometer is inaccurate, I'm reading it inaccurately, and I have an approximation of the true state of affairs. Now, if I continue to measure, and I measure lots and lots and lots of times, that level of lack of knowledge will get less. In fact, if I measure infinitely many times, it goes to zero. So I can reduce what we call lack of knowledge or epistemic uncertainty by working harder, by understanding better what's going on in the natural world. Those two kinds of uncertainty are recognised by lots of disciplines, including ours. So where did these things emerge in these tools that you've just seen about stakeholder analysis and the tables about likelihood and consequence and the priority setting and the mental models and the estimation of the value of a decision and the actions that are associated with different options and so on? Where does the uncertainty belong? Because it's there, you know it's there, and how do you put it in and how do you deal with it? Well, they're worthwhile questions. Before we embark on an answer, I'm going to introduce a third and important sort of uncertainty that typically is ignored in treatments of park planning and decision-making generally in conservation biology, and that is what we call language-based or linguistic uncertainty. It's pervasive, in many circumstances it dominates the problem, and yet typically we ignore it. I remember when we first wrote a paper about this back in the early 2000s, Helen Regan is a senior author, mathematician in the United States. We got a review back that said, well, you learned about words in high school. It's insulting to tell scientists about language. This should be rejected. And yet, in most disciplined treatments of uncertainty, there is no careful analysis of the different ways in which people understand the language that is used in an analysis. I have seen reports in which the words scant and minor were used to describe the seriousness of hazards. And I have no idea to this day which one was larger than which other. The report didn't say. Clearly the author had a belief in which word was bigger and which was smaller, but it didn't tell us. Now, there are many kinds, but there are four kinds of language-based uncertainty that are most important for us. Ambiguity, words have two meanings. Vagueness, which means words have borderline cases. It depends on a high risk or a very high risk. There are some judgments that will be on the borderline between high and very high. And where I put them really depends upon how I feel about things. And there are rarely cases that are clearly high and another case which is clearly very high, and everybody would say the same thing. Under specificity, it means I know something about this problem, I just didn't bother to tell you. Context dependence, I didn't tell you the context in which these words were meant to be understood. An oil spill could be large if it's in a pond, and small if it's in an ocean. And I didn't tell you where it was. And so I have no idea what the word large means in that context, and so on. Now, language-based uncertainties can be treated with careful definition of terms, arbitrary thresholds, such as if you have 50 individuals, you're considered to be critically endangered. If you have 51, you're no longer critically endangered. I mean, the difference between 50 and 51 in most cases is arbitrarily small, but we make that arbitrarily sharp distinction between critically endangered and endangered to make the system work. Okay. Here's an example. We saw just a few moments ago in Greg's presentation. We've got categories of high, very high, medium and low. We have on one axis the threats and on another axis the things we care about. Now, an expert will put a hazard in the box and say, well, I think it's medium. If you give that to a different expert, you know, and I know, you're going to get a different pattern of greens and yellows and reds across that matrix. It depends on who you ask. Primarily in our experiments, 80% of the variation between experts is due to their different understandings of the words that describe the hazards that are presented. It's linguistic uncertainty. It's essentially arbitrary, and we just didn't bother to get rid of it. It's laziness, it's professionally negligent, but we do it anyway. We should fix this. We could fix it tomorrow. We think it's beneath us. We don't bother. We should treat this. The second thing is that the remaining variation is due to natural variability and epistemic uncertainty and layers of personal value that determine how we perceive and react to subjective judgments. I'm going to take a brief excursion to psychology. We know from 30 or 40 years of research in cognitive psychology that the attitudes we have to judgments about putative facts, I'm not talking about value-based assessments here, I'm talking about our assessments of probabilities and consequences of putatively factual outcomes, are determined by how a question is framed, the level of personal control we think we have, our understanding, how dreadful it seems, how fair it seems, how visible it is, and so on. There's a long and interesting list of these things that lead to very curious and powerful human behaviours when it comes, and these are behaviours of scientists making judgments about facts. I haven't even got to the value-based part yet. It leads to a bunch of behaviours that we could almost typify as a pathology, as symptoms of a kind of a disease: anchoring, availability bias, base rate neglect, confirmation bias, overconfidence, sunk cost bias. There's a long and oh my goodness, I just destroyed something. Sorry, sorry. I just done what everybody else has done. Yeah. Thank you. Thanks. There's a long and fascinating list. I'm just going to look at one of these because it relates particularly to a point that Marina made: motivational bias. This is I use this figure because it reminds me of an experiment done by a sociologist at Duke University about 15 years ago now. She asked a bunch of turtle biologists in North America, do you think turtles can be harvested sustainably? And she got a range of answers from, yes, let's try by doing the sort of fisheries forestry model, through to no, under no circumstances. And it didn't matter if they were NGOs or university or government, she got the same range of answers. And then she asked a clever question. She said, do you think that your opinions are factual and objective? And do you think the opinions of those who disagree with you are emotional and value-based? And almost everybody said, yes, I am rational, they are emotional. What we see is a clear demonstration of what we call a motivational bias. We invest in technical judgments, a belief that is born of our personal attitudes to a decision. It's inescapable, and typically we're unaware of it. So we need to know this about ourselves when we come into this process. So, who you are and your personal values, attitudes, your stake, your prospects about a decision will influence your judgments about facts when it comes to judgments and decision making. So here now we're confronted with the problem that Eddie just outlined so nicely. We have acts or actions, he called them. And these are the only things that ought to be prioritised. I agree with you. So I want to prioritise, which act am I going to choose, Act 1 or Act 2? And I have two states of the world, and I don't know which one is true. I have some belief in one, I have another belief in another, and Eddie talked about beliefs, and these are the outcomes, the things that I care about, the fundamental objectives in the language of Craig. If I can specify the probabilities of these states of the world, and I can quantify my outcomes, I can calculate the expected value or the expected utility of each of those acts. And a rational person would choose the act that maximises expected value. There's a theorem for this, it's been around for a couple of hundred years. If you do anything else, I'm going to take your shirt. It's just the right thing to do in an abstract and rational world. This is the way in which economists would teach us to do this business. Unfortunately, we don't know exactly the outcomes. As Eddie pointed out, the whole machinery of inference is about saying, what do I think is going to happen if I choose Act 1 and the state of the world is 1? Well, I'm not sure exactly. So, this is an example of such a circumstance. We did a survey of Kithar National Park in Pakistan, Pakistan's oldest and most iconic national park. There was a possibility of harvesting ibex, Sind ibex in that national park. I'm not a fan of harvesting, but it's not my decision. Their job was to estimate how many could we harvest. Well, it depends upon the state of the world. If the monsoons don't come, and you harvest, the population is going to decline substantially, and that's a bad thing. So the expected value under that state is poor. If the monsoons do come, I can harvest. What do I do? Why would I want to harvest? Because I can generate $5,000 per head, and I can run a national park off 100 animals. So there are some costs and some benefits associated with these two actions. If I encapsulate those costs and benefits in this table, this decision table, I can estimate the expected value. However, I'm not sure exactly whether... I do know the probability that monsoons won't arrive is about 10%. But I don't know exactly how many animals I'm going to get. I have an estimate, and it has some variability around it because it's naturally variable, and because I don't know everything about the system. I lack knowledge about the system. Those two kinds of uncertainty are embedded in my judgment. That the element in that cell that currently says 1 in the top left-hand corner under State 1 and Act 1, it's not actually 1, it's some other number, it's some interval. I might say, well, it's between 1 and 2. I don't know what it is exactly, but it's not going to be less than 1, it won't be more than 2, somewhere in there. In fact, every one of those cells is uncertain. Not only that, I'm not absolutely certain about the probability the monsoons will return. I've only been recording data for 40 years, and the rest is anecdotal. I know it's somewhere in the vicinity of 10%, but I don't know it exactly. What do I do with this? Well, you can still make rational and, in some circumstances, robust decisions. You can clearly define what the right decision is, even under circumstances in which you have substantial natural variation, substantial lack of knowledge, and a suite of alternative actions in states of the world. This is a sensible, simple way to encapsulate what it is that you don't know about the world. Because if you leave it out, if you give it a colour, or you give it a single value, you're essentially submerging that uncertainty beneath the surface. And our human propensity is then to ignore it. Unless you bring it to the surface and make it visible, you'll simply override it, and you'll make bad decisions as a consequence. There are ways of making good decisions, like the max-min rule and other interpretations of that general thing, that can lead us to very robust decisions, even under extreme uncertainty. These tools of this kind, can be embedded in these broader tools of decision making that were invented originally by Eisenhower and the United States Army back in the 1940s. This is not new, this has been around a long time, that allow us to specify the things that we care about, the fundamental objectives, in a hierarchy that establishes what it is we care about and how these things are structured, so that we don't double count, so that we don't leave anything out, so that we have these things clearly and unambiguously defined and specified. And we have a measure of each thing that represents fairly and clearly what it is that we care about and how it is going to respond to the actions that we might change. that architecture exists. It's existed for, at least in our domain, especially in Canada, the United States, with the Fisheries Department and other places, as Eddie pointed out, for at least the last 10 years or so. But this architecture has been around for about 40 years. We should use it. If we're not using it, I believe we're not doing our job right. Thank you.